Dear friends, in this video lecture again we are going to solve few of the numericals based on the concepts of radiation, and the first one is on the board. At first we will read this and then go for the solution for this one. Compare the rate of emission of heat by a black body maintained at 727 degrees centigrade. The temperature of the black body is 727 degrees centigrade, and to convert it into Kelvin we have to add 273. Therefore, the temperature of the body is 1000 Kelvin. 727 plus 273, it should be equal to 1000 Kelvin. This is T1. The black body is initial at a temperature of 1000 Kelvin, and then the same black body is thereafter, it is at the temperature of 227 degrees centigrade, and to convert it into Kelvin it should be equal to 227 plus 73, 300 plus 200, it should be equal to 500 Kelvin. And this is kept in a surrounding. The temperature of the surrounding here is the temperature of surrounding enclosure, and it is 27 plus 273, it is equal to 300 Kelvin. This is the data given to us. Now compare the rate of emission of a heat. This is one thing that we have to compare. According to Stephen's law of radiation, the quantity of radiant heat emitted per unit time per unit area, that is, the rate of emission of heat per unit area, is directly proportional to the fourth power of the absolute temperature. Therefore, I will write here is R1 upon R2 is equal to T1 to the power of 4 divided by T to the power of 4. The reason is very simple, because this rate of emission is directly proportional to the fourth power of absolute temperature, and in order to remove the proportionality constant, we have to take a Stephen's constant here, but Stephen's constant in the numerator and denominator get cancelled, and therefore what remains here is R1 by R2 is equal to T1 to the power of 4 divided by T2 to the power of 4, and it should be equal to 1000 to the power of 4 divided by 500 to the power of 4, and therefore we will get R1 by R2 is equal to 1000 divided by 500. 1000 divided by 500 to the power of 4, it should be equal to 1000 divided by 500 is 212 to the power of 4 is 16. Therefore, the rate of emission R1 at temperature T1 and rate of emission R2 at temperature T2, these two have a ratio of 16:1. Therefore, the answer is 16:1 for the comparison of rate of emission of a heat. Now, thereafter we will go for the comparison of rate of loss of heat. Then from the Stephen's law of radiation, we know that the quantity of radiant heat emitted will be sigma T to the power of 4. And if it is kept in a surrounding of temperature T0, it will absorb a radiant heat sigma T0 to the power of 4. Therefore, the rate of emission of heat, I will write it as dQ by dt. This is the loss of heat at temperature T1 divided by the loss of heat at temperature T2 per unit time is dQ by dt2. Now, as it is directly proportional to T1 to the power of 4 minus T0 to the power of 4, it is T2 to the power of 4 minus T0 to the power of 4, it should be equal to 1000 to the power of 4 minus 300 to the power of 4 divided by. Here it should be 500 to the power of 4 minus 300 to the power of 4, and it should be equal to. Here we will take 10 to the power 2 common. Therefore 10 to the power 2, 10 to the power 2, 10 to the power of 2, 10 to the power 2, 10 to the power 2 power of 4 means 10 to the power of 8. It will be common in the numerator, it will be common in the denominator, and that will get cancelled. And therefore what we will get here, 10 to the power of 4 minus 3 to the power of 4 divided by 5 to the power of 4 minus 3 to the power of 4, and it should be equal to 10,000 minus 81 divided by 625 minus 81, and it should come out to be equal to 9,919 minus it should be equal to 544, and this total comes out to be equal to 18.23. After solving this one, we will get this one, 18.23. This is the required answer. Okay, we will go for the next one. The next problem is very simple. It is based on Wend's displacement law. Wend's displacement law stated that the radiations emitted by the black body consist of different wavelengths, and out of that, for a particular wavelength, the quantity of radiant heat emitted will be maximum, and the particular wavelength at which the quantity of radiant heat emitted maximum is lambda m, which is inversely proportional to the absolute temperature of the body. Therefore lambda m is equal to V divided by capital T. This is the Wend's displacement law, and the problem here that we have written on the board is to be solved from the Wend's displacement law. For that, what we will do? Now, Earth's mean temperature can be assumed to be, the temperature is assumed to be, here its value is 280 Kelvin. Earth's mean temperature is supposed to be 280 Kelvin. Therefore, capital T is equal to 280 Kelvin. 280 Kelvin. Find out lambda m. Therefore, what this lambda m equal to, the value of capital B is not given in the book, in the numerical, but we know that it is equal to 2.897 into 10 to the power of minus 3, and divided by the value of lambda m is 280, and the total comes out to be equal to, after solving this one, you will get this as 1.035 into 10 to the power of minus 5 meter. This is the value of the wavelength of radiation at which the maximum amount of radiant heat is emitted, and this value lies in the microwave region. This lambda lies in microwave region. This is the answer for this, the given numerical. Hereafter we will go for the next one. Dear friend, this is again a problem which is based on Stephen's law of radiation. Here I will read the problem there first, and then we will see how to solve this one. A small blackened solid copper sphere of radius 2.5 centimeter is placed in an evacuated chamber. A solid copper sphere is kept in an evacuated chamber. The temperature of chamber is 100 degrees centigrade. at what rate the energy must be supplied to copper sphere to maintain its temperature at 110 degrees centigrade. Given that Stefan's constant is 5.67 into 10 to the power of minus 8 joule per meter square per second per Kelvin to the power of 4. Here friends, there is a little printing mistake in the book. In the Maharashtra textbook it is given 5.76, but it is not correct one. It's 5.67. At the most you can take it as 5.7. Therefore a little mistake, and that too it's of operator, not the writer. It's a printing mistake. We can ignore that, and as we know the value, we will take it as 5.67 into 10 to the power of minus 8. Now, how to solve this problem? For that, the rate at which the heat is lost is given by it is equal to sigma A T to the power of 4 minus T0 to the power of 4. Now, this is the rate at which heat is lost if body temperature is more than that the temperature of the surrounding. Here what we expect here is that the temperature of the body should remain 110 degrees centigrade and temperature of surrounding is 100 degrees centigrade. Therefore, we have to take the loss of heat here, and therefore it is equal to sigma into 4 pi r square. As it is a solid sphere, the surface area of the solid sphere is 4 pi r square. The sphere has a radius r, therefore its surface area is 4 pi r square. It is t to the power of 4 minus t0 to the power of 4. We will write the values hereafter. We will put the values here. Sigma, as I have said, it is a Stefan's constant. It is 5.67 into 10 to the power of minus 8. The temperature of the body is to be maintained at 110 degrees centigrade. 110 plus 273. It should be equal to 383. This is 383 minus T0, 100 degrees centigrade. 100 degrees centigrade, 100 plus 273, it is 373. Now this raised to 4 minus this raised to 4, we will write it in a square bracket. Here it is remaining that, therefore it is 4 into 3.14 into radiuses of 2.5 into 10 to the power of minus 2 whole square. Only thing that we have taken here is sigma, then we taken the 4 power, then we have taken the area. Only the interchange of the terms taken here, 4 pi r square. It should be earlier, but it is written later. यहाँ पे एक थोड़ी सी गड़बड़ ऐसी हो गई है कि यहाँ मैंने सिग्मा लिया है, यहाँ पे t to the power 4 लिया है, t0 to the power 4 लिया है. ये मैं भूल गया था एरिया 4 पाई r स्क्वायर है. ये भूले हुआ एरिया मैंने इसको बाद में जोड़ दिया है मल्टीप्लिकेशन में. तो मल्टीप्लिकेशन में कोई दिक्कत आती नहीं है, अपन पीछे आगे पीछे कर सकते हैं. ओके, इसके बाद अपन आगे चलते हैं कैलकुलेशंस के लिए. Then it comes out to be equal to 5.67. Then again I will come here. It should be 12.56 4 pi. Then it should be fourth power of 2.5. Square of 25 is 625. Then square of 625 is it is 2.5. Oh, sorry. Here I should take it as a square only. Square of 25 is 625. Therefore, square of 2.5 is 6.25. then I will take it as 10 to the power of minus 4. No, thereafter I will take here 10 to the power 2 common, 10 to the power 2 and 4th power of that. It is 10 to the power of minus 8. Here 10 to the power minus 8 and this is 10 to the power of 8. And this is 10 to the power of minus 4. This is 10 to the power of minus 8 and 10 to the power plus 2 common here and 4th power of it is 10 to the power of 8. And what remains here is square of 8, 3.84 and square of that means 4th power of 3.84. 4th power of 3.84 is 215.17 minus and 4th power of 3.73 it is 193.56. बच्चों यहाँ पे मैंने 4th पावर डायरेक्ट लिखा है तो आपको क्या करना पड़ेगा कि ये जो 4th पावर निकालना है तो इसका पहले स्क्वायर निकालो और स्क्वायर का और एक बार स्क्वायर निकालो तो 4th पावर बन जाएगा. You can do it by log table or you can do it by calculator. In log table, there is a very good method. Multiply the log of this number by 4 and take an anti-log of that. That you will get the 4th power. Like that, again rearranging the terms, we have taken all the values here, 10 to the power of plus 8 and 10 to the power of minus 8. Here in multiplication, there is a addition of the indices. Plus 8 minus 8, it will be 10 to the power of 0 and 10 to the power of 0 is 1. Therefore, we will take it as 1 in multiplication. And what remains here is 5.67 into 12.56 into 6.25 into subtraction of these two, and the subtraction of these two comes out to be equal to 21.61 into 10 to the power of minus 4 and the total comes out to be equal to इसका अपन गुना करते हैं तो जो आंसर बनेगा आप इसको कैलकुलेटर से करने के बजाय लॉग टेबल से करिए. इन लॉग टेबल वी हैव टू टेक addition of all the terms of logarithmic of all the values and then take an anti-log. The answer come out to be equal to 9618.50 into 10 to the power of minus 4 and ultimately it comes out to be 0.9618. It is heat required per unit time, therefore it should be watt. This much energy should be supplied to the copper sphere so that you will get the constant temperature of 110 degrees centigrade. Now we will go for the last problem or numerical in this session. We will solve this one and it is based on When's displacement law. It's very simple. The peak value of emissive power is possible at a certain wavelength and that is lambda m, and this lambda m is inversely proportional to the absolute temperature. This is the formula and here we have given the peak values of the wavelength. One is 700 nanometer. It's in visible spectrum of radiation, 700 nanometer. The second wavelength is given 3 centimeter. It comes out to be in a microwave region. And third one is of a longer wavelength. It is of 3 meter. It is FM radio wave. आपको पता होगा कि रेडियो पे जो सिग्नल्स आती है उसकी वेवलेंथ ये बहुत ज़्यादा होती है. मैंने हमारे बचपन में एक बार बहुत बार ऐसा सुना है. ये ऑल इंडिया रेडियो का विविध भारती स्टेशन है 25 और 41 मीटर बैंड पे. तब मुझे पता नहीं चलता था कि वो 25 मीटर क्या है और 41 मीटर क्या है। तो 25 मीटर यानी 25 मीटर वेवलेंथ की वेव्स वहां पे वो रेडियो अपना रिसीव करता था और उसके ऊपर प्रोग्राम बनते थे और वो हम बचपन में सुनते थे। अभी भी अपने टीवी पे आते तो UHF अल्ट्रा हाई फ्रीक्वेंसी वेव्स और VHF वेरी हाई फ्रीक्वेंसी वेव्स आती है। तो FM पे लॉन्ग वेवलेंथ की वेव्स आती है। तो इसकी FM रेडियो वेव्स की वेव्स आती है 3 मीटर पे। विविध भारती पे बहुत अच्छे प्रोग्राम बनते थे, पिक्चर की गाने आती थी और हम वो सुना करते थे। तो वो बहुत अच्छा होता था और वो मुझे अभी भी ट्यून याद है। ये ऑल इंडिया रेडियो का विविध भारती स्टेशन है। 25 और 41 मीटर बैंड पे, 25 और 41 मीटर ये वो बैंडविड्थ होती थी वेव्स की, जिसके ऊपर एक प्रोग्राम आता था इलेक्ट्रोमैग्नेटिक वेव्स की। ठीक है, तो अपन इसे शुरू करते हैं। हियर क्या है वो वेरी सिंपल थिंग, Wiens displacement law, lambda m is equal to b divided by capital T, and that is capital T is equal to b divided by lambda m. The first we will take the temperature for this 700 nanometer. It is equal to 2.897 into 10 to the power of minus 3 divided by 700 nanometer means 700 into 10 to the power of minus 9. 11वीं में अपन पढ़ते हैं कि ये जो है वो मल्टीप्लिकेशन फैक्टर होता है। नैनो मीन्स 10 to the power minus 9, pico means 10 to the power minus 12, micro means 10 to the power of minus 6, milli means 10 to the power minus 3, kilo means 10 to the power plus 3. So it's a multiplication factor. Nano is a multiplication factor. It is 10 to the power of minus 9 and it comes out to be equal to 2.897 divided by 7. अभी क्या होता है यहाँ 10 to the power plus 2 minus 9 minus 7 minus 7 जब ऊपर जाता है तो plus 7 minus 3 10 to the power of plus 4. It should be equal to, the value comes out to be equal to 4138 Kelvin, 4138 Kelvin. This is the answer and it's very simple. You have to divide it by 2.897 by 7. 0.74 are 28, 7 ones are 1. Carried 2, 7 3s are 21. Like that you will get the answer. The second we will calculate capital T is equal to. Again we will make use of the same one. That is 2.897 into 10 to the power of minus 3 divided by. Next one is 3 centimeter. It is 3 into 10 to the power of minus 2, and it comes out to be equal to, it comes out to be equal to 0.9657, it is 10 to the power of minus 1, this much K. This is one more answer that we will get for 3 centimeter wavelength. And the third and last one, it is equal to 2.897 into 10 to the power of minus 3 divided by, the value is 3 meter. We will write here 3 only. It should be equal to 0.9657 Kelvin. These are the temperatures for these corresponding values of peak wavelength. And like this, we have taken few of the problems on radiation, and in the previous video lectures we have taken it on kinetic theory. मुझे पता है कि ये sufficient नहीं है, लेकिन just to know how to solve the problems, we have taken these one. I expect you will try more and more from the different books. As I had said, I'm ready to help you if you got any difficulty. In this video lecture, in the last clip, rather in the last slide, I'm going to give you a mobile number. You can WhatsApp on me on that number or you may call. But it's advisable. मुझे बच्चों से ये रिक्वेस्ट करना है कि एकदम बे टाइम फ़ोन नहीं करना. प्राइवेट लाइफ होती है, वो भी डिस्टर्ब नहीं होनी चाहिए. तो आप व्हाट्सएप पे आपका मैसेज डाल सकते हैं. मैं इसके बाद में आने वाले क्लिप पे मेरा नंबर छोड़ दूंगा. Thank you very much. I'm expecting more views from the students so that what I'm going, it should be beneficial to all. Thank you very much.